All right, fluid balance 2 is considerably shorter than fluid balance 1, so we should be able to get through this pretty quickly. You said no, it's not?
So 2 slides.
Oh, 2 slides. Not that short. We're going to list important sources of acids in the body, talk about how protein buffers and the carbonic acid buffer system, which you already know about, resist pH changes, describe the influence of the respiratory system on acid-base balance, talk about how kidneys regulate hydrogen and bicarbonate ion concentration in the blood, distinguish between acidosis and alkalosis resulting from respiratory and metabolic factors, and describe the importance of respiratory and renal compensations in maintaining acid-base balance. All right. So chemical buffers and respiratory regulation rapidly minimize pH changes. So the 4 goals of fluid balance and homeostasis is 1, keep the right amount of fluid in the 3 fluid compartments. We need to keep the right amount of total dissolved substances in that fluid. We need to keep the right amount of each individual substance in the fluid as well. And then keep the right amount of hydrogen ions and bicarbonate ions in order to maintain a normal blood pH. So going with each one of those goals here, remember that the fluid compartments are the intracellular fluid plus the interstitial fluid and the plasma that are considered the extracellular fluid. The right amount of total dissolved substances in the fluid, what did we say was the total osmolality of the 3 compartments? 300 milliosmoles. We need to keep the right amount of each individual substance in the fluid, so make sure you pay attention to how much sodium we have in each compartment, how much calcium, how much potassium, chloride, and protein. And then what is the normal blood pH range that we should stay in between? 7.35 to 7.45. All right, so proteins function at a specific pH. You should already know this from not only this class, but B32 as well. Activation of enzymes relies on pH. What is one of the enzymes we talked about this semester that relies on acid or a pH change in order to be activated?
Pepsin?
Yeah, pepsin. So pepsinogen only gets converted into pepsin when it is in the presence of hydrochloric acid and it's a low pH environment. Also, what is the term for when an enzyme experiences a pH outside of its normal range and it starts to unfold? Denature. So pH will cause activation of enzymes, but also denaturation of enzymes if it's not within its optimal range. pH is a scale of hydrogen ion availability and presence. So please make sure, oh man, you wrote that down already, right? Okay. Why do you do this to me? What is this? I have no idea what this is. No, stop. What? I don't know what that. I'm not trying to rehearse. Okay, but we're still recording. She's going to jump up across a bunch of different slides. Okay. I hate technology sometimes. All right, there we go. So the higher the pH, that environment is more basic and has less hydrogen ions. The more acidic, the lower pH, and more hydrogen ions that are available. So make sure that you remember that, because a lot of people do get that mixed up. Like when we had that question regarding Valsalva's maneuver and whether it was a decrease or increase in pH, a lot of people got that mixed up and told me an increase in pH. And even would put like increase in hydrogen ions. Well, yes, it is an increase in hydrogen ions, but that means that it's a decrease in pH. So make sure you know those are inversely related. So low pH is high hydrogen ion. High pH means low hydrogen ions. What is an acid? It is something that dissociates in fluid, and when it does dissociate, it releases a hydrogen ion. And we just talked about the difference between a strong acid and a weak acid. Make sure you know strong acid is a complete dissociation, and weak acid is only a partial dissociation. So strong acids give away all of the hydrogens it has to give. Weak acids will only give off one of its two or three. And so we said that pH needs to be between 7.35 and 7.45. If pH is less than 7.35, that is considered acidosis. If pH is greater than 7.45, that is considered alkalosis. All right, everyone okay here? Okay. So next we're going to talk a little bit about bases. If it lets me go to the next slide. All right, so what is a base? Bicarbonate is a base we talk about a lot. Ammonium is as well, but we don't talk really about that much. We'll talk a little bit about how proteins can act as bases as well. But this is going to help keep our pH of both our body and body fluids and blood. So one thing that you did not know before, we talked about how blood needs to be between 7.35 and 7.45, but actually each space is going to have its own normal pH, and there actually is a difference in pH between arterial blood and venous blood. So in the intracellular fluid, you're going to see a pH of closer to 7.0, so neutral. Inside the interstitial space, you're going to see a pH of about 7.35. And then for blood plasma, venous pH is going to be a little bit lower because it has more CO2. So we said before that more CO2 means more hydrogen ions. And so venous blood, which has a higher CO2 content, is going to be a little bit lower in pH. Versus arterial pH is closer to the average, 7.4. Oh, and I didn't. Oh, it's already in your lecture notes. Look at me. All right, so how are acidic products produced in the body? CO2 leads to carbonic acid, like we see with our carbonic acid buffer equation. More CO2 on this side is going to shift the equation to the right, which is going to make more carbonic acid, which is going to eventually make more hydrogen ions. Phosphoric and sulfuric acid are a result of protein breakdown. Lactic acid from anaerobic respiration. How many ATP do we get from anaerobic respiration? 2. Just 2. And where does anaerobic respiration take place? Cytoplasm. We get fatty acids from fat breakdown as well. And then ketone bodies are produced when glucose cannot enter the cell in adequate amounts and alternate fuels like fats are burned instead. And what type of chemicals are ketone bodies? What kind of chemicals are ketone bodies? They're acids. We're just talking about acids. They're organic acids. Everyone okay here? This should already be in your lecture notes. Okay. So before we move on to the next slide, there's a little note in your lecture notes that the respiratory system works directly on the left side of the equation. So we can make changes in CO2 values by breathing either faster or slower, and we'll talk about that later. But the respiratory system is going to take care of changes on the left side of this equation, while our kidneys are going to be more of the acid-base balance on the other side. Again, that's already in your lecture notes. So our buffer system, and this is in the order in which we use them. We use chemical buffers first because they're fast acting, like that bicarbonate buffer system. Then we have the respiratory system. This is going to take several minutes to start after the chemical buffers are saturated. So once we've already made adjustments to pH as much as we can with our chemical buffers, then we have to rely on our respiratory system to make changes in our breathing in order to help balance our pH. If that does not work, if that's not sufficient enough to work, then the kidneys will take over that pH balance, and that's a long-term mechanism. So we rely on chemical buffers first, then we rely on our respiratory system, and then last resort is our kidneys to do long-term pH regulation. So we're going to talk about each one of those things in order. And then, let me see. No, we're going to talk about those next. Okay. So chemical buffers and respiratory systems rapidly minimize pH changes. So we have our bicarbonate buffer system, which is one of our chemical buffers. And again, chemical buffers are the first line of pH regulation. They can act within a fraction of a second to resist pH changes. And so our bicarbonate buffer system, you already know. If we have, how do I want to say this? Yeah, so if we have too much, and let me see if it goes in the other, oh yeah, it does, okay. So if we have too much hydrogen ions, let's say we have a low pH, we have too much hydrogen ions, what is going to happen is we're going to use this bicarbonate buffer equation to combine those hydrogen ions with bicarbonate ions to make carbonic acid. And then you should already know that the enzyme carbonic anhydrase is going to convert that into some CO2 and water. And then we can eventually get that CO2 to diffuse into the cells of our lungs so that we can breathe out that CO2 in the atmosphere. That's one way that we get rid of hydrogen ions. We convert all of that to CO2 and then breathe it out in the atmosphere, and now we've effectively dropped our pH. However, there's only so much bicarbonate that we have available in the body that these will get saturated at some point if our pH is much too low. And that's when we would have to rely on more on the respiratory system to make changes in the breathing rates that we have. And then lastly to our kidneys. I think that's it for that. We also have a couple other buffers that we use chemically. So we have the protein buffer system because we have amino acid side chains on our proteins that can act as buffers. When you learned about protein folding in B32, you learned that the side chains, some can be positive and negatives, and that can direct the folding of those proteins. Sometimes there are hydrophilic and hydrophobic ends. And there are some that are acidic, and some that are basic as well. And so we have some amino acid side chains on our proteins that can act as buffers. Okay, so we can rely on this bicarbonate buffer system. We can rely on protein as well. We can rely on phosphates as well. But this is the main one that we're going to be talking about because this has been a recurring thing that we've talked about throughout the entire semester. Okay, so you can even see at the very bottom it says a phosphate buffer system will not be discussed. It will be talked about in your textbook, but we don't need to talk about it here. So when chemical buffers in the blood are saturated, we've used all the bicarbonate that we can to try to eliminate those hydrogen ions. Then the respiratory rates are going to go up to get rid of even more CO2 if the blood is acidic. Why? So, let's see if I have any extra notes there. Oh yeah, we're just going to go here. Okay, so what if blood is acidic? So if blood is acidic, it's going to have a pH of less than what? 7.35. Which means that we have too many hydrogen ions. And so, which way do you think this equation is going to move in order to lower the amount of hydrogen ions and increase our blood pH? Is it going to move to the left or to the right? To the left. Okay. We're going to take those hydrogen ions again, combine them with bicarbonate ions, which this should have a negative, make some carbonic acid, convert that to CO2 and water, and the CO2 is going to be eliminated through our respiratory system. Okay. How we can make this happen even faster is just by increasing our respiration rate. So we increase our respiration rate so that we're getting rid of more CO2 than we normally would at rest. Okay, so our breathing rate increases. So we shift this to the left even more and continually get rid of that CO2 in order to bring our pH back up. So as a result of increasing our respiration rate and breathing out excess amounts of CO2, that's going to bring our pH back up to normal and bring these hydrogen ions down in order to reach homeostasis. All right. So what if blood is alkaline? What would be the pH if blood is alkaline? Greater than what?
7.45.
Greater than 7.45. I'll do this in a darker color. Greater than 7.45, which means that we are going to have a low amount of hydrogen ions. And there always should be a balance. And so in that case, if we need more hydrogen ions, which way is this equation going to go? To the right. So what we're going to do in response to that is we're going to lower our respiration rate. And if we lower or we slow down our breathing, we're going to be holding on to more CO2. So CO2 levels rise. We convert more of that with water to carbonic acid. And then that's going to dissociate into hydrogen ions and bicarbonate ions. But the important thing is that we're getting more of these hydrogen ions. More of those hydrogen ions mean a lower pH, higher amounts of hydrogen ions, and we can bring us back into that normal range of between 7.35 and 7.45. So everyone okay with that concept? Make sure you know this is going to be a multiple choice written exam, so just make sure you're really comfortable with which way that equation is going to move in which situations.
Like the whole thing?
Yeah, but it'll be multiple choice, so that equation will be given to you. You just got to know if we move to the right or left for acidosis and alkalosis. All right, so what happens when we have hyperventilation? And there's Will Smith. I remember that episode. It was really funny. But hyperventilation. So with hyperventilation, know that when we say hyperventilation, we don't just mean increasing our breathing rate. It's more of an out push of air than breathing in. So it's like really short in breaths, but big out breaths. So like, so it's not an even in and out. It's more out than in. Okay. So this is hyperventilation. And if we're hyperventilating and getting rid of a lot of CO2, which way are we forcing this equation? To the left or to the right? To the left, because we're getting rid of the CO2. Okay. So with hyperventilation, we have increased respiration. And again, more out than in. So what we're doing is we're increasing our CO2 offloading. We're getting rid of large amounts of CO2. But the thing is, the trigger for hyperventilation for the most part is emotional stress. Okay? Like, I always give the picture of Rachel breathing into a paper bag on Friends when she leaves her man at the altar. But usually when you hyperventilate, it's a emotional trigger. You have a big presentation to give and you freak out and you're hyperventilating because you're not ready for it. And so when this happens, normally you already are in homeostasis and then you hyperventilate because of some emotional trigger, and now this puts you out of homeostasis. So you're increasing your respiration rates when it's not required. So when we're forcing this equation to the left, our hydrogen ions are no longer free floating like they should be because we're getting rid of them through CO2. And so this leads to, is this going to lead to a increase in pH or a decrease in pH? Increase. And so what you're doing by hyperventilating, or what you're putting yourself at risk of, is physiological alkalosis. Which is why when people are hyperventilating, they give you a brown paper bag to breathe into, because going into alkalosis, one of the symptoms or the effects or consequences of that is passing out. And so by giving you a brown paper bag, you're not really getting rid of that CO2, because you breathe it out, then you immediately bring it back in. And so by bringing that CO2 back in and not really eliminating it, it helps you to bring your pH back down to normal, or to prevent that alkalosis or prevent the passing out.
They tell them to slow down the breathing.
Yeah.
Slow down.
So you can capture more of that CO2 and bring your pH back to normal.
I have a question.
Yeah.
Can it also happen if you're not hyperventilating, where you pass out?
I mean, you could pass out for a number of reasons.
Like a vagal response?
Yeah, of course. Yeah. That's one of the signs of hyperventilation, that you can pass out due to that. But there are many different reasons for passing out. So questions about hyperventilation. So you're basically putting yourself into alkalosis, and you're doing this hyperventilation when your body didn't need it. All right, so renal regulation, which is the last thing that we look to for pH balance. So again, first chemical buffers like the bicarbonate buffer system, then changes in respiration rates, and then we look to the kidneys to regulate for us. And so when we're talking about kidney function and kidney regulation of pH, we're going to be regulating this side of the equation in order to balance the pH. And ammonia is sometimes used as a buffer as well, but we're not going to talk about that too much. We're going to talk more about bicarbonate today. So your body produces mostly hydrogen ions and secrete those hydrogen ions when we have too much of it. We reabsorb bicarbonate in order to keep that pH balance. And so the kidney tubules indirectly reabsorb bicarbonate from the filtrate and manufacture new bicarbonate within the tubule cells in order, again, to keep this pH balance. Acidosis is much more common than alkalosis. You're more likely to build up too many hydrogen ions than you are to build up too many bicarbonate ions. So we either secrete those hydrogen ions out directly, or we secrete it out with ammonia and get rid of it that way. So if we have too much hydrogen ions, we get rid of it in our urine through secretion and then just reabsorb more bicarbonate ions. If we have too little hydrogen ions, we're going to reabsorb the hydrogen ions from the filtrate and then put the bicarbonate in the urine. So it all just depends on where we are at that time. If our pH is too low, we're going to reabsorb more bicarbonate. If our pH is too high, we're going to reabsorb more hydrogen ions. But know that generally the body constantly produces hydrogen ions, so it must secrete hydrogen ions and reabsorb the bicarbonate to prevent acidosis. That is much more common than getting into an alkalosis situation, because of all the ways we listed of how we produce acids. We produce those way more than we produce buffers. So again, this bicarbonate buffer equation, this is another reoccurring theme all semester long, so make sure that you feel really comfortable with it. So CO2 combines with water within the tubule cell. You can see that here, forming bicarbonate or carbonic acid. That carbonic acid is quickly split because our cells are filled with fluid. Our cells are filled with water. So as soon as carbonic acid is formed, it's going to immediately split into its parts. So then it splits into its hydrogen ion and bicarbonate ion. And then the hydrogen ion is secreted into the filtrate because, again, acidosis is much more common than alkalosis. in most people. And so the normal physiological response is to get rid of the hydrogen ions. And then the bicarbonate is then moved towards the blood to be reabsorbed. So you can see we're secreting hydrogen towards the urine or filtrate, and we're reabsorbing bicarbonate in the other direction. So for each hydrogen that's secreted, a bicarbonate enters the peritubular capillary blood either through symport with sodium or antiport with chloride. Now I won't ask you about that, just know that it's being reabsorbed while the hydrogen ion is being secreted. The secreted hydrogen ion is then going to combine with bicarbonate in the filtrate, and then that's going to make carbonic acid. And then with the use of carbonic anhydrase, we're going to split that water and CO2, and then that CO2 can be transported either into the cell to facilitate more of that split and secreting of hydrogens and reabsorbing of bicarbonate, or it can be moved into the blood. So it's really just this cycle of using this equation over and over and over again to maintain this pH balance. We already just talked about that. The carbonic acid is formed in the filtrate and dissociates to release the CO2 and the water. CO2 diffuses into the tubule cell where it triggers further hydrogen ion secretion. So again, just this cyclic over and over to get rid of hydrogen ions to make sure that we maintain a pH balance. All right. Do I want to talk about this? Let's skip this. I don't ever ask about it. All you need to know is that we're getting rid of hydrogen ions and we're making new bicarbonate all the time. Okay? Why give you something that I'm not going to test you on? This is the one time though. Let me see. Did I talk about this when you took the class, Shai?
What?
About the formation of new bicarbonate ions?
In a specific area or
Yeah.
just in general?
No, in this area. I don't think I did. With ammonia and stuff? No. Sometimes I get a little overzealous with what I want to talk about. Okay. So if alkalosis occurs, which again, it's more common to have acidosis versus alkalosis, but if alkalosis occurs, then we're not going to secrete those hydrogen ions because we're going to need them in order to bring our pH back down. And then what we talked about last time, or did we talk about? Oh yeah, we just talked about it at the end of this last lecture. So we said that with aldosterone, whenever we bring in a sodium, we bring in a chloride as well because the positive and negative balance each other out. And if we're in alkalosis, and we said before, if we're in acidosis, sometimes we'll switch that chloride for a bicarbonate if we're acidotic, so that we make sure that we're also balancing pH at the same time. But if we're in alkalosis, we're definitely going to be bringing in that chloride instead of more bicarbonate. Okay, so it's all going to be based off of what our pH is at the time. Because if we're in alkalosis, we're not going to be bringing in more buffer. That doesn't make sense. That would bring the pH even higher. So instead, we're going to bring in the chloride like we usually would. All right, this is the last little bit of a concept here, and this is going to be one of the very few times where I'm going to tell you exactly how I'm going to ask you this on the exam. It'll be exactly the same for you as well with Professor Green. Okay, so these are the normal blood gas results for pH, CO2, and bicarbonate. So pH should be between 7.35 and 7.45. You already know that. CO2 should be between 35 to 45 millimeters of mercury, and bicarbonate should be between 22 and 26 milliequivalents per liter. You're going to be given this on the written exam. It'll tell you these are the normal values. Then you will be given a patient's values, and then you're going to tell me, is it metabolic alkalosis, respiratory alkalosis, metabolic acidosis, respiratory acidosis, or none of the above. Okay, so you'll be given the normal, then you'll be given patient values, and then you're going to give the diagnosis. Okay, so we're talking about respiratory acidosis first. So with respiratory acidosis, you can expect, now, so if we're in acidosis, what would you expect the pH to be compared to normal? Less than 7.35. If we are in acidosis, Now, one thing I'm going to say here. If it's a respiratory issue, you're going to see CO2 out of range. Okay? And bicarbonate should be normal. If it's a metabolic issue, then you're going to see bicarbonate out of range. That's how you're going to know whether it's respiratory acidosis or alkalosis or metabolic acidosis or alkalosis. So again, if CO2 values are off, it's a respiratory issue. If bicarbonate values are off, it's a metabolic issue or a kidney issue. Okay? So, that being said, with respiratory acidosis, what would you expect the bicarbonate levels to be?
22 to 26.
22 to 26 is going to be normal. If it's a respiratory issue, bicarbonate is going to be normal. What values that are going to be off are the respiratory values. So this should stay normal, which is the 22 to 26. Now, CO2. If you are in acidosis, would you expect to have too much CO2 or too little CO2?
Too much.
Too much. So it should be greater than 45 millimeters of mercury. So when you're coming up to these questions, first you want to look at pH. Is pH high or low? There are going to be some examples on some of these versions of the exam that the pH is normal. It'll say that pH is 7.41. Then you're going to immediately go none of the above. It's none of them. So make sure that you look at pH first. Because if pH is normal, then there's nothing else to be done. There's no diagnosis to give because their pH is normal. Okay? That's the first thing you want to look at. Then, after you look at pH and you notice that pH is low, so you've already determined it's acidosis. Okay? Then, after you determine it's acidosis, then you're going to look to the CO2 values and the bicarbonate values. If the bicarbonate values are normal and the CO2 levels are off, it has to be respiratory acidosis. If the CO2 levels are normal but bicarbonate is off, then it's metabolic acidosis. So look at pH first, determine if it's acidosis or alkalosis, and then look to the CO2 or bicarbonate values. Okay. So normally how you may see this is if respiratory rates have decreased. So let's say you have something like COPD, okay, where you can't get old air out, you're holding on to a lot of CO2. CO2 rises, it forces the equation to the right, and you make more hydrogen ions. That's how you get an acidosis, respiratory acidosis, is by a lowering in respiration rate due to some kind of respiratory dysfunction. Okay, let me see what the lecture notes say so I know what to write down, what not to write down. So it says at the very top, respiratory acidosis may result from impairment or slowing down of normal respiratory functions, like in the case of severe asthma, emphysema, or other forms of COPD, shock, trauma, or hypoventilation. Okay, so that's when you would see respiratory acidosis. So is everybody okay with this example? Okay. So next slide, respiratory alkalosis. So in respiratory alkalosis, what would we expect the pH to be? Greater than 7.45 is alkalosis. What would we expect the bicarbonate levels to be?
Lower.
This is respiratory alkalosis, respiratory. So what would bicarbonate be?
Oh, same.
22 to 26. It's going to be normal. If this is a respiratory issue, it should be your CO2 levels that are off, not your bicarbonate levels that are off. So what should your PCO2 be then? Less than 35. Because we said that too high of CO2 is linked to high hydrogen levels and low pH, so this would be the opposite. If you're in alkalosis, it's because you have not enough CO2. But honestly, you don't even need to know that, really, because you're going to be given the normal values. Again, you're going to look at pH first. If it's acidosis, then you'll know it's acidosis, but then you're just going to see, are the CO2 levels in range? If they're not in range, then it's respiratory acidosis or alkalosis, whichever one that you determined in the beginning. if the bicarbonate levels are out of range, and it's a metabolic acidosis or alkalosis. So you make sure you look at pH first, then you look at which values are out of range to determine whether it's a respiratory issue or a metabolic issue.
So the pH and the CO2 are always gonna be opposite of one another?
Yes, so high CO2 means low pH, low CO2 means high pH, yes. All right, so this may happen with the example that we just gave earlier, is with hyperventilation. If you're getting rid of too much CO2 because you have this emotional trigger that causes you to hyperventilate, you are forcing this equation to the left to allow you to release all of that CO2 back out into the atmosphere. So you're getting rid of those hydrogen ions, which is going to increase your pH here. But if you breathe into a brown paper bag or slow down your breathing, get that person to calm down, then their pH levels should normalize. Everyone okay with this example? Okay. So metabolic acidosis. What would you expect the pH to be? What was
Greater
that?
than 7.45.
With acidosis?
Less than 7.35.
Less than 7.35. It would be a low pH for acidosis. What would you expect the CO2 levels to be if this is a metabolic issue? Normal or 35 to 45? Because this is not a respiratory issue. This is a kidney or metabolic issue. Now, if you're in acidosis, do you think you have too much buffer or not enough buffer?
Not enough.
Not enough. So it'd be less than 22 milliequivalents per liter. Is everybody okay with that concept? Okay. Why you might be in metabolic acidosis could be due to your chemical buffer system being overwhelmed. Okay. That didn't work. Respiratory system buffer didn't work. Now you're trying to rely on your kidneys, and that may not even be enough, or they may need more time to compensate. Large amounts of acids were produced, like with diabetes mellitus, or if you're on a keto diet, or if you are starving and your body has to look for fats to make energy, then you might develop more ketone bodies and lots of acids build up. Large amount of acid was ingested, so if you take too much aspirin, that can cause acidosis as well. Or large amounts of bicarbonate were lost from your intestinal mucus, like you had diarrhea or excessive vomiting or things like that caused you to get rid of a lot of bicarbonate. Those are all possible. One more. And lactic acid built up from anaerobic respiration. So all of these things are possible ways to develop metabolic acidosis. Everyone okay with that example? Okay, last one is metabolic alkalosis. What would you expect the pH to be with somebody with alkalosis?
It's gonna be
Greater than 7.45. If this is a metabolic issue, what would you expect the CO2 levels to be? Normal, or between 35 and 45 millimeters of mercury. And if you're in alkalosis, do you think you have too little or too much buffer? Too much. So it would be greater than 26 milliequivalents per liter. And I have the bicarbonate highlighted this whole time because these are new values that you haven't really seen before. So with metabolic alkalosis, some causes of that include ingestion of too many alkaline substances, like if you take too many antacids or milk of magnesia. We said before with digestive that Tums should not be something that you're taking chronically. It should be for like one-off heartburn. Or excessive vomiting. When stomach cells make more hydrogen ions, remember that alkaline tie will continue to put more bicarbonate into the blood. Okay. So any questions on that? So again, on the final exam, you're going to be given the normal values. You're welcome. Okay, they'll already be there for you. So make sure you look at pH first. If pH is normal, none of the above. Move on. Do not overthink it. Okay, because if pH is normal, there is no issue. You guys promise? If pH is normal, you're going to put none of the above. You're not even going to think about it anymore. Okay, good, because people overthink all the time. Okay, look at pH first. Okay, Once you determine if it's acidosis or alkalosis, then you look at the other values. If CO2 is out of range, it's respiratory. If bicarbonate is out of range, it's metabolic. Okay, you're going to get about 2 or 3 questions on that in exactly that format, where the normal values are given, then you're given patient values, and then you have to diagnose. Okay, any questions on that? Okay. Another thing that I don't test on is compensation, so do not worry about compensation. We can go ahead and skip that. You guys have enough to study. I know Professor Green won't ask about that either, so you guys are good here. Any questions? And that is it for fluid balance, and we've just